Hello, in this video we'll begin our discussion of Chapter 22, in which we'll compare two groups. In practice, it's much more common to compare two groups than to test whether a single proportion or mean is equal to a given number. So let's start with section 22.1, the standard deviation of a difference. Recall, for independent random variables x and y, the variance of the difference x minus y is equal to the sum of the variances, the variance of x plus the variance of y. So the variation increases even for the difference of two random quantities. This means the standard deviation of x minus y, which is the square root of the variance of x minus y, is the square root of the variance of x plus the variance of y. So we'll start by focusing on two groups in which we're computing a sample proportion for each group. So we're looking at the difference between two proportions. These two samples will most likely have different sample proportions and different sample sizes. So the two sample proportions will denote by P1 hat and P2 hat, and the two sample sizes will denote by N1 and N2. We'd like to know what is the standard deviation of P1 hat minus P2 hat. Let's use what we just discussed about the variance of a difference. The variance of P1 hat minus P2 hat is equal to the variance of P1 hat plus the variance of P2 hat. And of course, the variance of P1 hat is the standard deviation of P1 hat squared. The variance of P2 hat is the standard deviation of P2 hat squared. By the central limit theorem, we know what the standard deviation of the sampling distribution is. So for P1 hat, it looks like this, the square root of P1 Q1 over N1. And for P2 hat, it looks like this, the square root of P2 Q2 over N2. So this reduces to P1 Q1 over N1 plus P2 Q2 over N2. And then the standard deviation of the difference, P1 hat minus P2 hat, will be the square root of the variance, so the square root of what we just found. We typically don't know the true values of P1 and P2, the true population proportions, so we'll use the sample proportions and we'll estimate the standard deviation of the difference. We'll call this the standard error of P1 hat minus P2 hat. So I'm just going to replace P1 with P1 hat and Q1 with Q1 hat. And so the standard error looks like this. Section 22.2 deals with assumptions and conditions for comparing proportions. So we'll start with the independence assumption. Within each group, the data should be based on results for independent individuals. Here we check the usual conditions, the randomization condition and the 10% condition. But because we're comparing two groups, we're going to have an additional independence assumption called the independent groups assumption. So starting with the randomization condition, the data in each group should be drawn independently and at random from a population. The 10% condition says the sample should not exceed 10% of the population. And this new independent groups assumption says the two groups must also be independent of each other. Finally, each of the groups must be big enough, so we need to check the success-failure condition. Both groups are big enough that at least 10 successes and at least 10 failures have been observed in each. In section 22.3, we learn how to construct a confidence interval for the difference between two proportions. Now we've already seen that for large enough samples, each of our proportions has an approximately normal sampling distribution. Well, the same is true of their difference. So let's talk about the sampling distribution of P1 hat minus P2 hat. Provided we've met the assumptions and conditions we just talked about in section 22.2, that is, provided the sampled values are independent, the samples are independent, and the sample sizes are large enough, we can predict the following about the sampling distribution of P1 hat minus P2 hat. For shape, the distribution will be approximately normal. For center, the mean is P1 minus P2. The true proportion for population 1 minus the true proportion for population 2. And for spread, the standard deviation is the square root of P1 Q1 over N1 plus P2 Q2 over N2. Let's look at how we construct a confidence interval, also referred to as a two-proportion z-interval. So we take the difference in our two observed sample proportions, P1 hat minus P2 hat, add and subtract this critical value z star based on our confidence level times the standard error of P1 hat minus P2 hat. So I've got an example to illustrate how we set up the confidence interval. So let's suppose we've got a group of individuals who are wanting to quit smoking, and they're going to use a nicotine patch to do so. But some of the individuals will also attend a support group. So we're going to randomly assign individuals to two groups. Group 1 will use the nicotine patch and attend the support group. Group 2 will use the nicotine patch and not attend the support group. So it turns out 46 of the 143 individuals in group 1 ended up quitting smoking to give us a sample proportion of 0.322. And 30 out of the 151 individuals randomly assigned to group 2 quit smoking to give a sample proportion of 0.199. We should start by checking the necessary assumptions and conditions. So if you start with the independence assumption, smokers were randomly assigned to the groups. It's reasonable to assume the two groups were independent. And then for the success-failure condition, in group 1, there were 46 successes. 46 of the individuals quit smoking, 97 failures. In group 2, there were 30 successes and 121 failures. And all of these are greater than 10. So let's start by calculating the standard error of P1 hat minus P2 hat. We'll use the observed sample proportions in place of the true population proportions. P1 hat is 0.322. Q1 hat would be 1 minus 0.322. And the sample size for group 1 was 143. P2 hat is 0.199. Q2 hat would be 1 minus P2 hat. And the sample size for group 2 was 151. So this gives a standard error of 0.051. Let's set up a 95% confidence interval. So we'll take the difference of our observed sample proportions plus or minus the critical value z star times the standard error that we just calculated. So here's the difference of the sample proportions. Z star would be 1.96, and we just found the standard error to be 0.051. So the confidence interval is 0.023 to 0.223. We can interpret our confidence interval as follows. We are 95% confident that the support group program could raise the proportion of smokers who quit by using the patch by between 2 and 22 percentage points. So next time we'll look at a hypothesis test for comparing two proportions.